Okay, so ready to start the next session. So the next talk is going to be on evaluating YJIT, and Maxime's going to give it. Thank you.
All right, hi everybody. So today I'll be telling you about our paper, evaluating YJIT versus performance in a production context, a pragmatic approach. So YJIT is a project to build a new JIT compiler for Ruby built inside CRuby. We started this project in 2020 at Shopify, but it is fully open source with significant contributions from people at GitHub. And we try to take a data-driven approach to optimization where we have a large, diverse set of benchmarks. We benchmark often, and we gather detailed metrics to inform our optimization decisions. YJIT is a team effort. It would not be possible without my amazing colleagues at Shopify and GitHub. The team is not that big, but we had several contributors over the years. The goals of the YJIT project are to be able to run any Ruby codes, to be 100% compatible with what we run in production at Shopify, to be able to produce double-digit speedups on real-world Ruby software with a focus on web workloads in particular. And as much as possible, never slow Ruby code down. So worst case, no speed up, but no slowdown either, which is not always trivial. And of course, it must be well tested and stable. We're seeing increased adoption. YJIT has been included as part of Ruby 3.1, 3.2, this year, version 3.3. We've already deployed it in production at Shopify on multiple internal services, including also public-facing services like Storefront Renderer. And it's been deployed on a few websites that you may know about, some that you probably don't know about. And there's also some internal testing at GitHub, so possibly eventually GitHub is going to run on YJIT. Why did we create YJIT? There's been many projects in the past to create Ruby JITs, including JRuby, TruffleRuby, and MJIT. But none of these ever really gained much traction, in large part due to practical obstacles. So TruffleRuby boasts the fastest peak performance, but in many ways it's still a research project. The initial focus was entirely on peak performance, and it is my personal view that they did not sufficiently anticipate or adapt to the needs of the industry, at least not yet. There's also some alternate implementation challenges in there. That is, if you create an alternate implementation of a language and you can't guarantee that you're 100% compatible with the mainstream implementation, people will hesitate to adopt your system. This is not just something that applies to Truffle. It's also been true for PyPy and LuaJIT. People have a lot of respect for the work that Mike Powell did on LuaJIT, but Lua keeps adding new features with new versions, and that makes users hesitate to adopt it, unfortunately. YJIT is based on a technique called lazy basic block versioning, which is something that I developed during my PhD at the University of Montreal. We've published 2 papers about it at UPSLA. It's a technique that tries to achieve type specialization without traditional type analysis. So traditional type analysis can be surprisingly expensive. It can consume a lot of memory and time. And you can also use what's known as a hybrid type analysis, but that requires de-optimization, which can also be expensive and unpredictable sometimes. So the question I sought to ask through my PhD is, can we do type specialization without traditional type analysis? The way that it works, I won't go into all the details, but it does lazy tail duplication or tail splitting, and it uses this as a device to propagate type information. So it's a little bit like lazy evaluation for code, where we generate code as late as possible to try to capture as much context to specialize the code as possible. And the goal is not to create multiple versions of code. It's really to use this as a device to extract type information from the running program. Compared to the work that I did in my PhD, the JavaScript JIT that I had built at the time was a pure JIT system. YJIT uses the CRuby interpreter as a baseline. It also has a multi-platform backend that supports both ARM64 and x86-64. It does runtime value promotion. It makes systematic use of speculation and code invalidation. And we also pay special attention to the memory footprint and gather detailed metrics. So JIT compilers are not just ahead-of-time compilers that run late. They have to juggle multiple trade-offs. There's the performance of the generated code, but there's also warm-up time, how long the JIT compiler takes to generate the code, the amount of memory that the JIT compiler itself uses. So you have to invest time and memory to generate optimized code, but the JIT compiler also has to pay for itself. But in return for all these trade-offs, we also get access to privileged information because we can observe the program while it's running. Many JIT compilers papers in the past have focused exclusively on peak performance, and they tend to completely ignore memory usage. The issue of warm-up time is sometimes swept under the rug a little bit, but the reality is that most people can't really ignore warm-up time. So often the warm-up criteria is just to iterate for as long as needed on benchmarks until peak performance is reached, and it doesn't matter if this takes several minutes, but this is not really a practical approach. So in this paper, we look at multiple metrics that we use to optimize YJIT with production in mind. And one of the twists, if you will, is that we use the CRuby interpreter as a baseline for both speed and memory usage. And we also look at warm-up time as how long until we can outperform the interpreter. The reason we do this is that the CRuby interpreter is the default implementation of Ruby, and we have to convince people to use our JIT compiler. So we have to be able to reliably outperform the CRuby interpreter if we want people to use YJIT. So YJIT warms up rapidly and predictably. The reason why this is important is that slowdowns are generally bad. People expect us to perform at least as well as the interpreter, but also sudden drops in performance can be really problematic, as bad as an embarrassing pause in a garbage compiler. Because if you think Shopify is running, for example, a lot of stores where people buy things, if you have a sudden slowdown and pages start timing out, not only is this bad user experience, but it also translates into a loss of revenue. Your website doesn't work correctly. So the JIT compiler must pay for itself. We have to be able to minimize compilation time. We have to amortize compilation time. One of the things that we do is we just use a really simple heuristic, which is we only compile a function once it's been called n times. It's really simple, but it also works surprisingly well. It has deterministic behavior. And we also took some steps to make sure that YJIT generates code as fast as possible, where we minimize the number of passes, we avoid dynamic allocations in the backend, etc. JIT compilers add memory overhead. Some of this is the machine code that you generate, but the bulk of the memory usage of YJIT is actually metadata that we store, so like type information, the optimization information, etc. One of the biggest optimizations that we've done to reduce memory usage is just to allocate. We used to allocate a large chunk of executable memory when the JIT starts, and then start to fill it up. But my colleague Alan Wood just implemented a technique where we lazily allocate this memory as needed instead, and that translates into a huge drop in memory usage just from this. We've also taken steps to optimize the memory used by YJIT's metadata. So YJIT uses a lot of context object to track type information at various points in the program, and we have antagonistic goals with this, where we want the context objects to be as small as possible, but over time we also want to store more and more information into these objects. So we have to represent this information compactly. The context object in YJIT is a flat object with no pointers, and we do some amount of bitwise arithmetic to say like we have 16 possible types, so we only need like 4 bits per type. We use only 8 bits to track register allocation information, etc., etc. So in this, I think it's useful sometimes to work backwards to say, I have a budget of n bytes for my context object. How can I use those n bytes as efficiently as possible? Benchmarks. Traditionally, the Ruby community before YJIT had a heavy focus on micro benchmarks, and there was one benchmark in particular that the Ruby community loves, which is called upcarriage, which is an NES emulator. It's a cool benchmark, but one of the problems is it's not representative of the code that people use in practice. It does bitwise arithmetic. It has these nice big functions that are easy to optimize. It's also like heavily monomorphic, no polymorphism. So those micro benchmarks test the easy case, for example, where you have no inline cache misses, but you also need to care in practice about how it performs when you do have inline cache misses. So before building YJIT, we started curating our own suite of benchmarks with the goal that every person who works on YJIT should be able, with just one command, to gather benchmark data very easily and efficiently, make it as foolproof as easy as possible. We have 3 categories of benchmarks. What we focus on in this paper is what we call headline benchmarks. They're based on real-world Ruby gems with an emphasis on web workloads and things that we use at Shopify. We also have some synthetic benchmarks, like opcaret and the language shootout benchmarks, and some micro benchmarks. I think it's useful to have all 3 kinds because they all provide interesting data points, as long as you don't focus on things like micro benchmarks. These are the 11 benchmarks that we focused on in the paper. Again, all based on things that we think are realistic workloads. The biggest one that we had in the paper had over 3,000 methods compiled. And without further ado, this is the performance in terms of time taken relative to the CRuby interpreter for all of the systems, the Ruby JITs that we looked at. And we see that, generally speaking, Truffle Ruby has the best peak performance, although this is not the case on every benchmark. YJIT is able to outperform the interpreter by a pretty big margin on every benchmark. And also, YJIT performs very competitively when compared to JRuby. This graph, I think, is one of the most interesting ones in the paper. It's our measurement of the memory overhead for all of these implementations. So our production engineers often came to us and they complained because YJIT has memory overhead that used to be about 10 or 20% extra memory on top of CRuby. And our production engineers would tell us that's problematic, that's too much. But you can see that the memory usage of JRuby and Truffle Ruby just dwarfs the memory overhead of YJIT by 1 order of magnitude, sometimes 2. And this is very problematic. This is part of what makes Truffle Ruby completely unusable at this time in a production context, at least for our needs. We've also looked at warm-up time. This is a graph of the time per iteration of each runtime versus the total time spent benchmarking. And what's nice about this is you can visualize how long it takes for each implementation to outperform the CRuby interpreter. Importantly, you can see that YJIT outperforms the CRuby interpreter almost instantly. The other runtimes take a bit longer, with Truffle Ruby taking somewhere around 2 minutes, which again, in a production context, can be problematic because it can translate into drop requests, etc. One of the comments we have from reviewers is that on benchmarks, we have speedups of sometime around 30% and 50% end-to-end speedups in production, and that this is maybe not that impressive when you compare it to some of the JIT compiler work that's been done for JavaScript VMs, for example. So some acknowledgement. So YJIT is a relatively simple JIT built by a small team. It's also a retrofit into an existing VM with a 28-year-old C code base. So that comes with its own set of trade-offs, and there's a lot of room for improvement. But at the same time, I think Ruby and JavaScript are not exactly the same game. JavaScript is a much simpler and smaller language. I know because I implemented a JavaScript JIT during my PhD. The semantics of Ruby are more dynamic and more complex, more difficult to optimize. But there's also a difference where JavaScript is browser-based code, whereas we focus on what runs in the server backend. And so some of our benchmarks do database requests, for example, which we can't optimize. But we don't shim our benchmarks. Like in our benchmarks, that we really do make those database requests. So that's time that we can't shave off. But out of curiosity, I was curious, like, what do people use these days to benchmark JavaScript? I found a website where they talk about like the Jetstream suite of benchmarks. And as part of this, there's benchmarks like this, which is like a poker game benchmark. And this benchmark is 100% monomorphic. It's easily inlineable. It does a lot of bitwise arithmetic, which is not something that typical web applications will do. And it uses almost no external data. So conceivably, you could port this benchmark to run on an Atari 2600 with 128 bytes of RAM. So of course, you're going to get a 20x speed up on this benchmark. Also, my colleague Takashi Kokubun has been working on profiling how much time we spend in a JIT versus the rest of the code. And what we can see is that on Rails Bench, one of our biggest benchmarks, the time spent in JIT compiled code is only 12.7% of the total execution. So we've succeeded at making a JIT that generates code that is like several times faster than the CRuby interpreter. But the problem is now that time is being dwarfed by time spent in external C calls and external libraries. So we're getting to a point where it's going to be an advantage to rewrite codes, rewrite code in Ruby if you want to get better performance. So now into our production deployments. Shopify storefront render is the infrastructure that renders all the Shopify stores. It's mostly written in Ruby. It runs over 4.5 million e-commerce sites. I can't publicly state how many servers that is, but it is able to serve over 1.27 million requests per second. So one of the challenges that we had in benchmarking SFR is that traffic varies based on time of day, region of the world, and world events. So people in different countries will shop at different stores, and also the traffic varies based on promotions that people do on social media. So you can't, like something that people do sometimes when they benchmark production deployments is they'll benchmark their servers before and then they turn on YJIT and they look at the time after. But that's not a fair comparison. To do a fair comparison, you really have to run both at the same time. So in every cluster across the world, we have machines that run YJIT, and we also have a control that runs the CRuby interpreter, and we also have stats machine that gather statistics without disrupting the total execution time. This is the performance on SFR in terms of response time versus the CRuby interpreter. We have like about a 15% speed up on average, but also very importantly, even on the slow SP99 requests, YJIT performs better, which really shows that we've done a lot to make it so that YJIT can compile fast. This is a graph of the speed up over time during the 48-hour window that we examined. And again, we're never slower than the CRuby interpreter, even on a P99 slowest request. We've also measured the amount of memory overhead that YJIT takes, and interestingly, you can see the metadata actually takes up more space than machine code. I guess I should note we've also made some steps to reduce the memory overhead of the metadata since this paper was published. And also, nowadays we're actually up to something like 25% speed up on our deployment. So some key takeaways: YJIT is fully compatible with existing Ruby code. In terms of peak performance, it's also very competitive with JRuby. YJIT has the fastest, most predictable warm-up. YJIT has the least memory overhead, and sometimes by a really long shot. This is crucial for our production deployments, and it's something that if Truffle and Graal cannot solve the problem of memory overhead, they can't compete, even though they have the fastest peak performance. And also, YJIT has gotten even better since this paper has been accepted, so we have higher peak performance, less memory usage, and faster compilation times. Thank you for listening.
Okay, we have a couple of moments, one or two questions.
Hey, as somebody who's also worked on JavaScript and Ruby compilation, congrats. Those are great results. Your reviewer is comparing apples and oranges, so good job on rebutting that. I guess the one question I have is, with a lot of Ruby's core being written in C, do you see that changing over time as YJIT gets stronger? Like, is it going to be something that you're going to have to do a lot more, writing Ruby itself in Ruby?
We hope so. Something that we want to look at as Ruby 3.4 is like giving people more tools to be able to do things like byte manipulation, so that they might be able to write some of the things that they wrote in C extensions in pure Ruby code.
Okay, cool.
Cool. Okay, let's thank Maxime for a great talk.
Thank you.